Welcome to Physical Properties of Remote Sensing. In this lecture, we're going to talk about the remote sensing process, energy sources for remote sensing, and we'll talk about interference in the atmosphere related to the transmission of electromagnetic energy, specifically atmospheric scattering, atmospheric absorption, and atmospheric windows. We'll cover electromagnetic energy and interaction with Earth objects, the spectral properties of objects, and conclude with spectral bands used in remote sensing and a coverage of the 4 types of resolution. So, remote sensing is defined by Colwell as the measurement or acquisition of information of some property of an object or phenomenon by a recording device that is not in physical or intimate contact with the object or phenomenon under study. So this diagram here shows 3 different types of platforms. An orbital platform, which would be a satellite orbiting the Earth, and then there are suborbital platforms, which would fly closer to Earth, an airplane here and a drone. And on each of these there would be an instrument that is attached. You can see that H is defined as the altitude above ground level. We have an IFOV, which is an instantaneous field of view. In this instance, it's represented by D, and the arrows showing 3 palm trees. This is the object area that's being targeted. So with a process of remote sensing, we need a source for electromagnetic energy. There is an interaction with a target. There is the sensor to record that energy or data that we work with. There's transmission, reception, and processing. There is the interpretation, which is done by a GIS analyst. And then there's the application of that data, which is usually being shared with a workforce or a public. So the energy source illuminates or provides electromagnetic radiation to the target of interest. Here's a diagram showing a general schematic. We have the sun at A, so this would be passive remote sensing. B is the transmission of that radiation through the atmosphere. There's interaction with the target at C. There's a sensor that collects the information at D. The recorded energy is transmitted to a processing station. We have an image interpreted to extract target info. And then there is an application, which is shown here as a typical GIS model. And there's also another satellite that you can see here, which doesn't have a letter on it. That is a GPS satellite. It helps to georeference orbiting satellites around the Earth. So here is a cycle, and it's a process. It's shown here as a workflow or diagram, and it is a circular process. So when we study models, we will lay them out in specific steps, and in the real world, you don't always start at a particular place. But for this class, what we will start with is a research question, and that would be over on the left, and so it is the information that we're going to be working with. We'll be assessing the information, and we're not really doing much with development or sensor or data. All of that is going to be accessed by us as students. Then there's processing, then data analysis is what I want you to do for your project, and then there's interpretation of that data. So again, we will be accessing Landsat imagery, and you have been in your modules and working with that data, and you aren't doing the processing. You're not doing radiometric corrections, and you're not doing the processing from the actual satellite, but you are doing data analysis. You're interpreting that analysis, and you're providing it as information in answering questions to the modules and doing your PDFs. Okay, I'm going to talk about energy sources. So this schematic is showing passive sensors, and the ultimate energy for passive sensors is the sun. and there is transmission through the atmosphere shown in the red arrows. There is an interaction with the ground, and this simple schematic is just showing you that there are different land types: forest, water, grass, bare soil, paved road, and then built up or urban areas. There's a reflection of that solar radiation, and there's a collection of the satellite. With active sensing, the source of the electromagnetic energy is a man-made device, and there are 3 examples here: radar, LIDAR, and sonar. So we have a radar in the upper left-hand corner, and it's showing a simplified radar antenna transmission through the environment and interaction with a target. There is a pulse that goes back. By knowing the physics of the speed of sound, you're able to create images based on radar. On the upper right is a example of LIDAR, and this would be LIDAR flown from a small aircraft. And you can see that the representation of this is showing colors of elevation of the urban area and the wilderness area it's flying over. And then at the bottom is an example of sonar, and this is sound waves. You can see the original waves that are transmitting as red curved lines bouncing off of the blue object, and then the green dotted curved lines are the reflected waves. Again, by knowing the speed of sound, you can determine the distance to objects. So all of this is based on the electromagnetic spectrum. And so remote sensing is going to use radiant energy from the different portions of the spectrum, all the way from radio waves as the largest down to gamma waves as the smallest. So this should be a review. Our eyes are visible to the visible light portion, and we also use infrared, microwave, radio, and ultraviolet in remote sensing. So there are physical features that can be measured with an electromagnetic wave. So this is giving you a general idea of the size difference, starting in the top with ultraviolet, visible, infrared, and then down on through microwave. At the ultraviolet and visible portions, we're looking at ozone, land cover use, and vegetation. When we move down into about 10 micrometers to 100 micrometers, that is going to be ground surface temperature and sea surface temperature types of analysis. And then the microwave energy, which is much larger, would be precipitation, sea surface winds, wave height direction, snow depths, soil water content, and vegetation biomass. So the type of research question that you're asking is going to drive the type of imagery that you will select. So here's an example, a schematic of the wave. Again, from the crest to crest of the wave is symbolized by the Greek letter lambda, and you can see here the visible spectrum. So we've been working with bands in labs, and the wavelength that you work with, you can find that information in the metadata. And remember, each band is collected in a portion of the magnetic spectrum. So wavelength is defined as the distance between maximums, or crest to crest, as shown here. It is a very periodic or regular pattern, and you have a comparison here of 3 different wavelengths: a lower, a middle, and a higher frequency. And frequency is the number of wavelengths that pass a certain point per unit time. The unit of the wave model is hertz, and it is defined as 1 cycle per second. The speed of light, which is c, is equal to the wavelength times the velocity. Okay, I'm going to talk about electromagnetic energy and our atmosphere. So waves are described by wavelength, frequency, and amplitude. So we've already defined wavelength. Amplitude is the height of the wave, and you can see here there's a line drawn through that periodic wave. So the height, or the amplitude, is really half of that full cycle. And frequency refers to how many pass a given point in a certain time. and the propagation direction of this wave is drawn to the right of your screen. So wavelength is the distance of separation between two successive wave peaks. Velocity is the number of peaks that pass in a given time. And so speed of light is a constant symbolized by c, and it equals velocity times wavelength. And the value of the speed of light in a vacuum is 3.0 times 10 to the 8 meters per second. So here's what happens when electromagnetic energy is interacting with molecules. There's three possible things that can happen. It's either reflected, absorbed, or it's transmitted. So remote sensing is picking up on the amount of reflection or radiation or emission from Earth. So you might recall that all objects have emission or heat. Anything above 0 degrees Kelvin or a black body has some sort of emission, and there are remote sensing tools and data sets that will pick up on that. But again, basically what we're looking at is reflection of energy from Earth's objects. So here are some things that can happen with reflection. So the amount of electromagnetic radiation that reaches the sensor is dependent upon not only transmission through the atmosphere, but what is going on at the surface. So there's two types of reflection, specular and diffuse. So with specular, we have smooth relative to the incident wavelength, and this is going to result in a mirror-like reflection. It's only reflected in a single direction. This is very idealized and doesn't really happen in the real world. What's more likely is diffuse reflection. So when energy is interacting off of a rough surface, there is going to be scattering. And so the two top images there would show you specular reflection, and this is mostly theory, and the bottom three images are what really happen in the real world. So absorption happens because there are gases and different chemicals in our environment. So it's a process where the electromagnetic radiation is absorbed by the atmosphere or the terrain, and then it's converted into another form of energy. So if we look at the diagram at the top, it is showing you absorption windows for nitrous oxide, symbolized by N2O, oxygen and ozone, carbon dioxide, water, and then at the bottom is just a general schematic of various atmospheric windows. If you look at the graph of wavelength versus solar radiation below the top schematic, it is showing you a curve of solar radiation at the top of the atmosphere, and then you can see that there are dips in that curve, and they're labeled with different absorptive gases that are causing those dips. O3 is ozone, H2O is water, etc. So in this diagram, the peaks are windows, and the troughs identify wavelengths that are heavily absorbed. So again, our y-axis is percent transmission. We have our x-axis, which is shown here in micrometers, and the windows would be the high areas. Those are the areas where an object is going to be reflecting energy very well, and then the absorption is going to be where the energy is not transmitted through our atmosphere. So some wavelengths of electromagnetic energy are absorbed and scattered more efficiently than others. So water and carbon dioxide and ozone have the strongest absorption. Clouds, carbon dioxide gases, and the ozone layer that surrounds the Earth are all very strong absorptive features. And then transmission is when light moves through a surface. If you look at the bottom diagram of energy versus wavelength, where the arrow is pointing, it's showing that radiation emitted from Earth is of a much longer wavelength and a much lesser energy than the other types of energy. And the one on the top, again, is showing those troughs and those peaks of windows and absorptive areas. So again, here's a diagram that we've looked at before. It's just showing it to you larger. So just for review purposes, you can notice that There are water and carbon dioxide peaks at approximately 1.2 wavelength, and then there are troughs at about 1.4 micrometers of wavelength. Another trough of water and carbon dioxide is at 1.8 micrometers. There's several others in this graph, just showing you that a little larger so it's easy to see. So with scattering, again, in the atmosphere, here's a representation of what happens. So we have incoming energy that is represented by the 3 large arrows, and then the gray curvature that you see represents ozone. And so then the lighter gray is our Earth's atmosphere. And what really happens with energy is that there's a lot of scattering. So we have gases, we have clouds, we have weather systems, we have man-made pollution. All of those things are going to scatter energy in our atmosphere. So there's also interference with the surface. So if we had a true specular surface, we would get a very smooth reflection. But rougher surfaces are going to have different effects on that incident wave, as you can see. So there's a big difference between rough and very rough. And these lines are drawn, you can think of them as water surfaces. So rough seas are going to have different electromagnetic reflection properties than smooth or calm flat seas. Rayleigh scattering is when the diameter of the matter's molecule is less than 0.1 of the wavelength. Mie scattering is when the diameter of the matter's particle equals the wavelength of the electromagnetic radiation. And then non-selective scattering is when the particles are 10 times greater than the wavelength. So an example, Rayleigh scattering would happen with gas molecules. Mie scattering, or Mie scattering, is going to be the scattering from smoke and dust. And then non-selective scattering is what happens with something large like water vapor. Incidentally, Mie scattering is what creates oftentimes very beautiful sunsets. So in areas where there's a lot of pollution, you can get very brilliant and bright sunsets. I'm going to talk about electromagnetic energy and Earth objects. So the surface types will produce a distinct spectral response. Leaves will absorb in blue and red because that's where the chlorophyll molecules are working, and that's the type of energy that excites the chlorophyll molecules, and it reflects green, and that's why healthy leaves look green to us. And healthy leaves also reflect infrared. You can see here that there are 4 types of energy coming into this green tree and also this leaf, and then it is showing that it reflects green and infrared very strongly. Water is a very strong absorber, and so the longer visible wavelengths are absorbed more than the shorter ones. And so blue and green are reflected from water, and that is a big reason why water appears blue or green. If we think about the color of ocean water, there's also a lot of variation due to plankton concentration, which is the floating plants in the ocean. But in general, water is a very strong absorber, and it will reflect blue and green the strongest. Here is an equation showing you the physics, very generalized schematic of what happens to incident energy. Remember, there's 3 things that can happen to incident energy. It's either absorbed, reflected, or transmitted. Okay, moving on to spectral properties of objects. So we have our spectral signature, which we've worked with now, and you can see here, again, we have wavelength on the x-axis and reflectance on the y-axis. And this is showing you the spectral curve for different materials. We have a man-made object in the dotted and dashed line of concrete. We've got soils and fields and shingles in the middle, and then at the bottom we have asphalt, artificial turf, and then the very bottom clear water, and grass goes through the center of this curve. What I want you to look at is that Clear water is the lowest curve that is shown here. Again, water is a very strong absorber, so it's absorbing most of the energy. Asphalt is more absorptive than concrete. So think about, what color is asphalt usually? It's black. And it's a very dark color. It absorbs a lot of energy, whereas concrete is usually a whiter or gray color, and so it's more reflective. So here's an example of curves for vegetation, soil, and water. And you can use this information in order to study the characteristics of these earth surfaces. So dry soil is going to reflect differently than wet soil. Different types of vegetation will have unique curves. And then again, water at the bottom. This is an example of clear water, and it is very, very low on the reflectance scale. Here are some curves for rocks and minerals, and you can determine the primary mineral type in soils, and this is used for a lot of geological explorations. And these are the different types of minerals that are listed here. There are hundreds that are available in the USGS Mineral Library. So here are some spectral reflectances for tree species. And you'll notice that you can determine difference in species. So spectral curves are a very exact, specific science. The data that we work with in our lab is pretty generalized, and that's okay because we're just learning how to use the tools, but there are housed and archived curves for different tree species. So review here, just a different schematic. I'm showing it to you in a different way. We have energy is going through our atmosphere. There is incident radiation that is interacting with the terrain at number 2. There's reflected energy, and then there's total irradiance at the sensor. Now, there are very sophisticated physics equations that you can explore. If you are going on to perhaps maybe a bachelor's or higher degree, you will study the physics of remote sensing. We won't cover that in this course, but it's there for you if you are interested. So I'm going to talk now about the spectral bands that we use in remote sensing. So spectral bandwidth is describing the wavelength within the electromagnetic spectrum, and it's used to create an image. Spectral resolution refers to the number of bands or channels, and they are an interval of the electromagnetic spectrum as well as bandwidth within the spectrum. So here's a schematic showing 2 different spectral bandwidths, one for a Landsat multispectral scanner and one for a Positive Systems ADAR 5500. So you can see that they both have 4 bands, and the top one has green, red, near infrared, and a second near infrared. And you can see that on the x-axis, those are the portions of the electromagnetic spectrum that they're collected in. And then the bottom one is showing blue, green, red, and near infrared. So make sure when you are looking at satellite imagery that you understand the satellite platform that it came from. You can search Google for all publicly available publicly available data. I say Landsat because that's what we use a lot in this course. But you want to make sure that you research and find out what the bandwidths are for your imagery. So here's an example of wavelength versus intensity. And FWHM is a concept of full width at half maximum. So this one here is showing you an example of 0.7 to 0.8 micrometers, or that could be also interpreted as 700 to 800 nanometers, just a different unit. So it's approximately 100 nanometer bandwidth. So what it means is that for the band that is being shown in this example, it has a spectral resolution of 100 nanometers, and it collects information best in the 0.7 to 0.8 portions of the electromagnetic spectrum. It has an intensity, or a maximum intensity, of 0.75 micrometers, which is shown at the top of this curve. So this is how we mathematically describe and graph spectral bandwidth. So spectral bands, if we add them into a GIS project, and you should recognize this as a schematic of what GIS layers are like, this is showing you a blue, green, red, and near infrared band, and it's showing you in parentheses the corresponding lengths of the electromagnetic spectrum. So for blue, it was information that was collected between 450 and 515 nanometers. Green was 525 to 605 nanometers. The red was 640 to 690 nanometers. And the near infrared was 750 to 900 nanometers. So you can put all of these together and make a composite, or you can analyze them individually within your ArcMap session. So when we talk about hyperspectral, now we're looking at hundreds of images. So this is a cube. And hyperspectral imaging collects and processes information across the spectrum. So if you look at, we have our depiction of a wetland and a location of the world called Sullivan's Island. If you look at the y-axis over on the left, the z-axis over on the left, this is representing 224 bands of information that were collected. On the right, it is ranging from 400 nanometers to 2,500 nanometers. So the near infrared image that you're seeing on the top is part of the data cube, and it's just one of the 224 bands of this hyperspectral image. So the goal of hyperspectral imaging is to obtain the spectrum for each pixel in the image of a scene, and the ultimate purpose is to find objects or identify materials or detect processes. So with objects, can you see some objects in this image? You can, wetland is labeled, but you can also see that there are roads, there are urban areas, there are trees, there's a sandbar at the top of the image. Identifying materials, urban is pretty easy to identify. Visually, we know that urban areas have a repeating pattern. Roads, buildings, man-made structures are very easy to distinguish between natural features. And then detecting processes, we could look at pollution, we could look at water quality, we could look at changing shoreline, we could look at the mineral content of the soil. These are just a few of the thousands of possibilities of analysis. So hyperspectral sensors will collect information as a set of images. This is showing you our X, Y. Those are your latitude and longitude coordinates. And then the lambda here is showing you the Z component, which is the number of bands. So we're really looking at a three-dimensional product. Even though you only see 2 dimensions or a flat screen, when you work with hyperspectral data, it's important to remember that you are working with a cube of data. Most of us don't think that way, so this can be a new thought process. So finally, I'm going to conclude with the 4 types of resolution. So there's spatial, spectral, temporal, and radiometric resolution. So spatial resolution is defined as a measure of the smallest angular or linear separation between 2 objects that can be resolved by a sensor. We've already seen a picture of an IFOV, and the IFOV of the sensor defines the nominal spatial resolution of the remote sensing system. So here's another schematic, and you can see that the IFOV is below the satellite image on the left. And again, we're measuring the spatial resolution of a remote sensing imaging system. So it's really the angle that is subtended by a single detector element on the axis of the optical system. So an IFOV has a solid angle through which a detector is sensitive to radiation. On the left, the IFOV is shown as a circle on the ground. And then on the right, you can see that one ground resolution cell has been colored in black. The swath width is the full length of the rotating device and where it is collecting information. So spatial resolution, when you lay them out side by side, you can see and appreciate the differences. Here's the same area, shown as the smallest spatial resolution is 0.5 by 0.5 meters, and that means that each pixel measures 0.5 meters on each side. Then we have a 1 by 1 meter, 2 by 2, all the way through to the 80 by 80 meter resolution. So when you look at all these images side by side, if you were to consider the 80 by 80 meter resolution, you wouldn't really be able to distinguish very many objects. You can just see shades of gray. As we get finer and finer spatial resolution, you can see objects more clearly. And then in the lower right is a comparison of what the instantaneous field of view would be for an 80 by 80 meter pixel. And then you can see that the other pixels are shown relative to that 80 by 80 meter. So here is another comparison of spatial resolution. We're looking across the top at field systems, water body, flat site, and a towel site. And then just comparing those 2 meter, 4 meter, 1 meter, and 15 meter resolutions. So you can see that with finer resolution, you can see more details, and the images become sharper and easier for the human eye to interpret. So here's an example of Florida Keys. On the very left, it's very pixelated, and we have a 17-kilometer spatial resolution. In the center, we have reduced it down to 9-kilometer spatial resolution, and then the one on the right is a 1-kilometer spatial resolution. The second type is spectral resolution, and it describes the ability of a sensor to define fine wavelength intervals. So the finer the spectral resolution, the narrower the wavelength range for a particular channel or band. So here is some representations of spectral resolution. So starting in the upper right, there is our full width at half maximum graph. On the left, we've also seen these diagrams, and it's showing you the wavelengths collected in each particular band. The bottom left is a single band of ADAR 5500 data, and then on the right would be that depiction of the different bands. And so those were all collected, blue, green, red, and near infrared were all collected at different spectral resolutions. So here's an example of a marina in the Ace Basin in South Carolina. And again, if you look closely, the diagram on the left is also shown in GIS layers on the right. And so blue was collected in 450 to 550, and you can check the x-axis and see that indeed the rectangle that is representing blue band, numbered 1 in that graph, is between 450 and 550 nanometers. So here is an example of spectral resolution of 1 by 1 meter, and it is being used to study deciduous versus coniferous forest. And this is green, red, and near infrared bands. Here's an example of our hyperspectral cube, and this is an Avaris data cube of Sullivan's Island. Here you have a lot more choices in spectral resolution. Now, you might ask yourself, well, why don't we always use hyperspectral imagery? Well, it is cumbersome to work with, it's expensive, and when you have this much information, you will have a slower processing time and you require more storage. So hyperspectral isn't always the answer for your research question. With temporal resolution, temporal means time, and it's defined as the amount of time needed to revisit and acquire data in the same location. When applied to remote sensing, this depends on the orbital characteristics of the sensor platform as well as sensor characteristics. So temporal resolution specifies a revisiting frequency of a satellite sensor. In general, high temporal is less than 24 hours to 3 days. A medium temporal resolution would be 4 to 16 days, and then low temporal resolution is greater than 16 days. The Landsat imagery that we work with in our workbook has a revisit time of 16 days. Here is just a schematic showing you that the Landsat data is collected every 16 days, so June 1st of 1999, June 17th, and then again on July 3rd. So temporal resolution is important when you consider your question. If you're comparing change, you want to compare anniversary dates. So if you are looking at something like leaf area index, you want to be looking at dates of the same season because, as we know, that there are different seasons according to latitude on Earth. This is an example of a MODIS leaf area index composite. So it took images that were collected between March 24th and April 8th in the year 2000, and it composited them together. So leaf area index is a measure of biomass or greenness, and that translates into plant productivity. So with an index, what you're doing is you're putting together composites of image in order to get a sense for a value. You will study NDVI, which is Normalized Difference Vegetation Index, in a future module, and you will also look at some water indexes. Here's another example of temporal resolution being important. This is a MODIS image of photosynthetically active radiation, and this is showing the amount of photosynthesis that is being performed by the different vegetation types in the United States. And then finally, radiometric resolution. It describes the ability of a sensor to distinguish objects viewed in the same part of the electromagnetic spectrum. So it's often represented by bit depth or sensitivity. So the typical sensors have 8-bit, 11-bit, 12-bit, or 16-bit depth per band. And the higher the bit depth, the higher the sensitivity and radiometric resolution of the sensor. So our data is 8-bit, which is 8 to the 2 or 256. So that refers to the shades of gray. So this chart is showing 1 through 8 bits, and each shade of gray is the bit number to the 2 power. And it is how finely a system can represent or distinguish differences of intensity. So most computer files are 8 bits, which is 2 to the 8th power or 256 shades of gray. So higher resolution gives us better subtle differences in intensity, and it also will you'll be able to pick out finer levels of reflectivity. There are limits because with higher radiometric resolution, you have more noise and in your information. So we've already talked about digital numbers when we talked about pixels, and in digital remote sensing data, radiometric resolution is referred to as bit data, and it's recorded in terms of digital numbers. So for 8-bit images, we have from 0 to 255. We start counting at 0, and that would be pure black, and 255 is pure white. So here is that representation of a portion of an urban area, and you can see that there are shades of gray on the left and their corresponding digital numbers in the boxes on the right. Here is a comparison of radiometric resolution laid out side by side. So when we look at 1-bit to 8-bit, with 1 bit it's only 2 options, black or white. And you can see that there is an increasing level of gradations of gray as we go from 1-bit to 8-bit. As we increase our radiometric resolution, we can pick out finer and finer details. So if you compare the 8-bit to the 1-bit, you can actually see that what might have looked like a road in the first 1-bit image is actually probably a track, probably of a athletic field. You can see variations in the water. You can see the shoreline very clearly. You can actually see the crowns of individual trees in that 8-bit image. So again, here are the shades of gray, 2 through 256. Remember, it's the bit number to the power. So 1 to the second power, 2 to the second power, 2 to the first power, 2 to the second power, all the way up to 2 to the 8th power. So it's 2 to the power of the bit, not 1. So in summary, here are the 4 types of resolution and some images to go with them. So we have spatial, which is the size of the field of view. This example is 10 meters by 10 meters. We have spectral, which is the number and size of spectral regions the sensor records in the data. This one's showing blue, green, red, and near infrared. We have temporal, which is how often the sensor acquires data. This example is every 30 days. And then we have radiometric resolution, and that is the sensitivity of the detectors to small differences in electromagnetic energy. And this is showing you 1-bit versus 4-bit versus 8-bit resolutions with their corresponding shades of black and white or gray. So with resolution trade-offs, the different spatial, temporal, and spectral resolutions are going to be limiting factors for the utilization of satellite image data for different applications. So it's a trade-off. You always need to decide, do you want spatial, temporal, or spectral resolution as your primary area of interest? And because of technical constraints, satellite remote sensing systems can only offer the following relationship between spatial and spectral. A high spatial resolution has a low spectral resolution. A high spectral resolution has a low spatial resolution. So what that means ultimately is that a system with high spectral resolution can only offer a medium or low spatial resolution. Therefore, it is necessary to find compromises between the different resolutions according to the individual application or utilize alternative methods of data acquisition. So there's 2 different solutions. You can lay emphasis upon the most important resolution, and this is in direct dependency to the application or your research question. And then you can accept the low attendant resolutions, or you can lay no emphasis and accept medium spectral, temporal, and spatial resolution across the board. I encourage you on your own to just explore. I just put this in here for your enjoyment, and think about the question, is remote sensing an art or science? And this is a YouTube video that explores Earth as art. And the PowerPoints are available on Blackboard, and I hope you enjoy. So this concludes physical properties of remote sensing. Thank you.